Good morning, everyone. Welcome to our fourth talk of SIBGRAPI 2021. I'm Afonso Paiva from Universidade of São Paulo, and I'm going to be the chair of this session. It's a great pleasure to me introduce our next invited speaker, Professor Gladimir Baranoski. Gladimir got his PhD in computer science at the University of Calgary in 1998. I met Gladimir for the first time a long time ago in SIBGRAPI 2006 in the city of Manaus. At the time, I was just a PhD student and Gladimir was already a professor in Waterloo. Since that, we became friends, and when possible, Gladimir always attends SIBGRAPI. He currently professor of the School of Computer Science at the University of Waterloo, where he has established his research group. In his career, Gladimir presented remarkable results in natural phenomena simulation. For instance, he was the pioneer in the simulation of aurora borealis and rendering of plasma, the fourth state of matter. He has also outstanding results in simulation of light interactions with natural materials, such as human skin, plant tissues, and recently snow. Gladimir is a hard worker and a very active researcher. He has publications in important journals and top-venue conferences as well, such as ACM Transactions on Graphics, Computer Graphics Forum, Eurographics, ACM SIBGRAPI, and so on. His research interests comprise topics of different fields, including computer graphics, remote sensing, and biomedical optics. He has also organized conference courses and published books related to his research work. Today, Gladimir will talk about the quest for fundamental biophysical data. Before we start, I would like to encourage the audience to submit your questions to Gladimir through our YouTube chat and through our Discord channel as well. He will answer all these questions at the end of the talk. Gladimir, thank you to advance this invitation. And now it's up to you.
Okay, first of all, thank you for the very nice introduction. I start to think, who is he talking about? So is that me? Thank you, Alfonso. I know that you are, a nice guy, a very good friend, and I was really, wow, is that me? Oh, thank you very much. But first, I'd like to say something in Portuguese here, okay? My native language, after all. É grande prazer, né, estar participando do SIBGRAPI novamente. Tá? A primeira vez que eu apresentei um paper em uma conferência foi no SIBGRAPI, em 1990. Também foi realizado em Gramado, organizado pela professora Carla, do Instituto de Informática da URGS. Professores hoje importantes na comunidade de computação gráfica, tanto no Brasil como no mundo, né, como Marcelo Walter, Manuel Menezes de Oliveira e tantos outros, foram meus colegas, certo? Nós tivemos um tempo muito maravilhoso naquela época, então é muito legal estar de volta. Okay, now let's then switch to English. So I hope I don't mess up too much my presentation here with the buttons and everything, but I'll try to be careful. So the title of my talk, okay, the quest for fundamental biophysical data. So nowadays we talk lots about big data and so on, and someone already said that we in computer graphics, we use big data from a long time. We just call it data, because we are used polygons and all these kind of things. But I'm going to talk something a little bit more specialized than that. So let's start with this quote. Greg Ward is a researcher in computer graphics, very well-known researcher. In one of his papers in SIGGRAPH, he put this quote: "Good science requires both theory and data. One is of little use without the other." And that's very important, not only for computer graphics, science in general. So the question that I would like to pose here, the main topic of this talk here, is that do we really have enough biophysical data out there? Because sometimes you get the impression that we go in the internet, use one of the search engines, and you can get anything that we want. It's not quite the case, and that's what we are going to be talking about here today. So this a brief outline of my talk. First, I'm going to talk a little bit about what our group does in this area, okay, and introduce some terminology. Then I'm going to put this problem more in a scientific context, why data is so important for us, okay? And then we are going to talk a little bit about the current situation, what can be done to improve it, if anything can be done, what could be our contribution, okay? And we are going to finalize with some final comments at the end as well. So a little bit of an introduction here. This problem of shortage of biophysical data, okay, that we are going to be discussing is not a problem that limited to a particular area, okay? It's widespread in different areas, in different fields. It's not something new. But today, during this talk, I'm going to use as the background predictive modeling of light-matter interactions, because it's the area that we have been working more intensively lately. Then we have more examples to provide and so on. So for those of you that are not very familiar with our group, we work in natural phenomena simulation, different areas. And lately, okay, the last 10, 15 years, we have been working more in material appearance models and light interaction models. By the way, all the papers or results and data that we are going to be discussing here during this talk can be found in our website if you are interested in check it out later, okay? So throughout the years, we have developed several models of light interaction with different materials. We use a first principles approach in our models, and they have been published in different venues, okay? Not only in computer graphics, but also in applied optics and remote sensing, because we are always thinking about using them not only for image synthesis, but in other applications. So one of the things that I would like to show in the very beginning, I would like to show a relatively short video about one of our models, okay, which is going to give you an overview of the approach that we use, some of the terminology that we are going to be using throughout this talk as well, and then give you a little bit of a perspective, how data can be very crucial for us in our work and to not only to develop the models, but also to evaluate them. Okay, so could you please play the video?
The striking diversity of human skin appearance can be readily perceived in the visible domain. However, there is much more to skin appearance than meets the eye. For example, photos obtained using cameras equipped with specialized sensors show distinct appearance features in the ultraviolet and infrared domains. While the ultraviolet enhancements of freckles and other pigmentation irregularities, it is regularly used in appearance-based interventions to increase sun protection practices. The infrared ethereal appearance of human skin is often employed in artistic imaging. In this work, we present Helios, a novel hyperspectral model for simulating skin appearance features using a first principles approach based on Monte Carlo methods. Within this framework, reflection, absorption, and transmission processes are simulated, and their responses quantified in terms of BSS-RDF by computing the distances traveled by light within the cutaneous tissues. Helios incorporates the main light-absorbing materials acting within the various skin layers in the ultraviolet, visible, and infrared domains. It also incorporates the main scattering materials found within these layers, such as large cellular structures, melanin-containing organelles known as melanosomes, and collagen fibers. Moreover, Helios accounts for the fact that melanosomes may form complexes of different sizes or appear individually dispersed within the epidermal layers of skin specimens with different levels of melanin pigmentation. In a proposed framework, a melanosome is probabilistically positioned on the fly within a given epidermal layer, and the traversing light ray is either absorbed inside the melanosome or scattered. In the latter case, the melanosome is discarded and a new one is generated. This process is repeated until the ray is either terminated or scattered outside of the layer. In the case of melanosome complexes, the same on-the-fly positioning procedure is employed, with the traversing light ray also interacting with the encapsulated melanosomes, where it can be absorbed. For more technical details involving the simulation approach employed by Helios, please refer to our paper. We evaluated Helios predictions through comparisons with measured data and experimental observations reported in the literature. When light traverses the epidermal layers, it may be subjected to multiple interactions with melanosomes and melanosome complexes, a phenomenon known as detour effect, that may increase light absorption by melanin in comparison with a homogeneous solution of this pigment. Conversely, the traversing light may not encounter a melanosome, a phenomenon known as sieve effect, that may reduce light absorption by melanin in comparison with a homogeneous solution of this pigment. Previous spectral models do not account for these phenomena, which affect the accuracy of predictions in the visible domain, notably in the blue end of the visible spectrum, where attenuation is dominated by the melanins. Moreover, a strong forward subsurface scattering behavior of the epidermis, notably in the ultraviolet domain, is properly simulated by the first principles approach employed by Helios. Since Helios accounts for the distribution of melaninated melanosomes, it can provide modeled results that closely approximate their measured counterparts in the ultraviolet and visible domains. It can also provide close approximations in the infrared region, where attenuation is dominated by water and lipids. The angular dependency of the spatial distribution of light interacting with human skin is also captured by Helios. Moreover, while surface reflectance dominates in the ultraviolet domain, subsurface reflectance dominates in the infrared, resulting in a more diffuse distribution of infrared light, which is also captured by Helios. Our modeled reflectance curves can be reproduced using the online version of Helios. We also generated images to further illustrate the predictive capabilities of Helios in the hyperspectral domain. For example, a progressive increase in the overall epidermal melanin content is followed by a fast convergence to low reflectance values in the ultraviolet domain, due to the strong attenuation effects of eumelanin and phenylanin in this region of the light spectrum. In the infrared domain, where the spectral responses are primarily determined by the absorption bands of water, a decrease in the water content of the cutaneous tissues results in an increase in the overall skin reflectance. Note that modeled results can be obtained not only for uniformly pigmented regions characterized by average pigmentation parameters, but also for non-uniformly pigmented regions characterized by distinct pigmentation parameters. The presence of pigmentation irregularities is accentuated under ultraviolet light due to the strong attenuation properties of the melanin-laden melanosomes in this spectral domain. Under near-infrared light, however, such pigmentation features are less noticeable and the specimen is characterized by a soft, more diffuse ethereal appearance. Note that the overall reflectance becomes less diffuse and the presence of pigmentation irregularities becomes undetectable at wavelengths characterized by stronger water absorption. We remarked that Helios predictions can be quantified in terms of BSS-RDF or BRDF. While a minor contribution of subsurface reflectance in the ultraviolet domain makes the differences between BSS-RDF and BRDF responses negligible, the major contribution of subsurface reflectance in the near-infrared domain makes the differences between BSS-RDF and BRDF responses quite noticeable. Finally, we remarked that Helios can be seamlessly integrated into rendering pipelines aimed at applications in the visible, as well as in the hyperspectral domain. We have presented a novel hyperspectral skin appearance model that accounts for the complex structure of human skin, as well as the particle nature and distribution patterns of its main light attenuation agents, in order to predictively simulate skin spectral and spatial responses in the visible, ultraviolet, and infrared domains.
Okay. Thanks for the video, playing the video. So let's talk a little bit about what would be our objectives during this talk here, what we're going to be talking about. So I'm not the only one working in this area. There are many people, and I'm sure that many people have encountered similar problems. So it's more like sharing some experience, okay, and illustrate some of these situations here, and so that we can have some background to discuss what we can do about that in the future. So the application areas, of course, we are here in a computer graphics conference, but we are also aiming at applications in other areas. You have been doing work in these areas, and I'm going to bring examples from those areas as well, like remote sensing, biomedical, optics, and other areas too. So a little bit of scientific context then for our talk here. So one of the main aspects is predictability. So what's the relevance for that? What is involved in that? So we can generate, for example, an image of the human iris, for example, and try to mimic the color of that iris, okay? For example, brown iris. And we can generate a believable image of that. We can also use a model, a predictive model, okay, to get that color attributes. So how do we know that the model is doing a good job or not? How do you know the level of correctness of those chromatic attributes? So in order to do that, we need to compare with measured data when this measured data is available, okay? So to have a kind of idea about the correctness. This is not something new. That has been done in many fields. In computer graphics, this really started in 1997, a seminal paper, panel in SIBGRAPI, talking about this, Donald Greenberg and others. So predictability is associated with the concept of fidelity. Another thing is that we want the model to be controlled by biophysically meaningful parameters. For example, if we are on the beach and there is water in the sand, you know, the waves come and everything, what happens? That sand gets darker, okay? So in other words, as we increase the degree of water saturation, we have lower reflectance. So that's a behavior that we find in nature, and the model should reproduce that using biophysically meaningful parameters. So why do we care about predictability? First, let's take a look from the computer graphics point of view. We have here the image synthesis pipeline, okay? And you know that there are several stages in this pipeline, and many errors can be introduced, okay, in this stage. In our case, we are looking at this particular stage, and local light interactions, they determine, for example, the final appearance of the material. So by using a model that has been tested, evaluated as a separate unit of this pipeline, we can reduce the number of errors. And because this model is controlled by biophysically meaningful parameters, we have a better control over the final image that we are going to obtain, okay, using this model. So from the computer graphics point of view, using predictive models, we can make the rendering process more automatic and less dependent on ad hoc parameters. What else this can help besides generating pictures, okay? Having models that are predictive make their scope of contributions much broader. So we can now are not limited to computer graphics, but we can also provide contributions in other fields. For example, and here is not an extensive list of fields and applications. I'm going just to point out a few of those. Applications in physical and life science, for instance, in the case of remote sensing. So models are used, for example, to aid the interpretation of information captured by satellites, for example, reflectance and transmittance from regions of vegetation, soils, to determine the biochemical content, biochemistry of these regions, and especially water content, okay? And this can also be used in broader efforts. For example, one of the problems nowadays that we have is that because of climate change and human activities, desertification is expanding all over the world. It's a big problem, and many scientific communities are making huge efforts to try to mitigate that. And remote sensing and the use of models can be instrumental to help in those efforts, can help those efforts. Another thing is that what we have here is that we can investigate several phenomena, okay, for example, at the plant level, from seed germination to, for instance, chloroplast movements. So for those of you that are not very familiar with this, just a quick example here. So we have, for example, species of plants that they have these adaptive mechanisms. For example, one of them is that if the plant leaves overexposure to light, the organelles contain chlorophyll, they kind of move and align around or close to the walls of the cell. On the other hand, if you don't have enough light, you want to capture more light, they have a more uniform distribution, okay? And then the end result of this is that the appearance of these leaves, for instance, they get kind of whitish appearance. So we can also use this in health science. For example, we can study process elicited by ultraviolet light, for example, vitamin D production that takes place in some layers of the skin. Okay, this has become very important nowadays. We talk about immune systems and how to strengthen immune systems to fight different diseases, including COVID and so on. Photocarcinogens, for sure, you know, have different types of skin cancer, including melanoma. And you have process like tanning, which involve, for example, the production of melanin through melanogenesis, and a process called hyperplasia, which involves skin thickening. So there are not too many groups who work in this area. There are still lots of unknowns, and one way to study that is using this in silico approach, using computer models. If we have enough time, we're going to be talking more about this towards the end of the talk. We can also have, for example, these models assisting, for example, the monitoring, screening, and treatment of different medical conditions. Here is a very simple example. We have here an infant, okay, that had jaundice, and this is not a very uncommon medical condition. So it's like around 60% of infants have this condition. And basically what we have a waste product called bilirubin in the bloodstream. And because the liver is not well formed yet, it cannot expel quick enough, and the substance starts to accumulate. If it gets to a level that's too high, it may be very dangerous. It can even cause brain damage. So one of the ways to address that is to expose the infant to light, particular light in the blue and green end of the spectrum. So this exposure to light makes that substance to break down and be expelled in a more easy manner, okay? And two interesting things to mention here. This photograph is the daughter of one of my graduate students that he was taken a long time ago. Maybe she's now a grown-up woman and things like that. Okay, and second thing, this treatment was discovered almost by accident. A nurse saw some kids improving, okay, when they were exposed to light. That happens in 1958. And this became like used only more than 20 years after that. So that can tell you more or less the time frame, how things evolve in science sometimes. So, what are the main ingredients to achieve predictability? First of all, there is no free lunch, okay? So if you want to simulate light interaction of material, you need to study that material. You need to understand the process that takes place within that material. So we need to devote time for that, go deep on that. For example, if you are going to simulate skin, you don't need to become a dermatologist, but you need to know a lot about skin optical properties. Also, keep in mind that we are not the only ones doing this. There are people from different areas working models as well. And why reinvent the wheel? Why not share information? So there is this cross-fertilization that we can use in our advantage. Third thing, we need to employ, okay, scientifically sound methodologies. Okay, for example, when we are designing a model, we want to choose the proper level of abstraction. So we can try to simulate in the atomic level what happens when light interacts with a plant leaf, but if you don't have data for that, what we can do? So we need to choose the appropriate level of abstraction. We need to evaluate, so we need to give an idea to people how good or bad the model is. And depending on that, we need to refine the model and get more data. So that brings us to that part. That's the main part of our talk here, the part related to data. Remember the first quote that I present here, good science requires both theory and data. One is of little use without the other. Well, in our case, what data we are talking about in this context? Let's say to have a model for plant leaves, for instance. And the first thing that we need is elementary data. For example, plants absorb light. So we need to know, for example, the absorption coefficients of these different absorbers like chlorophyll, carotenoids, water, and so on. We need to know the refractivity index of these components. That would be the elementary data. Second thing, we need to know something about the sample itself, its thickness, the concentration of this pigment, the concentration of water, and so on. Finally, we would like to have data to evaluate this model. So then we can compare, okay, the model and the measure curves. In an ideal world, these models that we are using here to characterize the sample have been obtained from the same sample, okay, that we use to get the evaluation data. And also in the ideal world, we can get this data anytime that you want. That is what would happen in an ideal world. But that's not what's happening in reality. In fact, we are very far from it, okay? So let me just get some water here. I hope I not talk too fast here and you can still understand what I'm saying, despite of my accent. But anyway, let's proceed. So first thing that we need to keep in mind is that reflectance and transmittance bases are very scarce. And even though I'm going to mention some problems here, I don't mean there's a criticism to people that came up with this database. They have their own needs, their own priorities. And in fact, I'm very grateful that at least they did something, otherwise we could not have done anything in this area. So besides the scarcity, what other problems do we face in this area? So usually the characterization data either is not there at all, or you have very simplistic, one could put in that way, description of the samples. Let's take a look, for instance, what happens with skin. Sometimes we see databases with spectral data for skin, and you have no description of the sample as being Caucasian, African, Indian, Asian, and so on. But what that means exactly? That means that Caucasian has light pigmentation and therefore has high reflectance. And for example, an African subject is darkly pigmented and low reflectance. If I show these curves to you, okay, here you have 4 curves from 4 different specimens obtained by in the same experiment. And if I ask you which one of them, which of these curves correspond to a Caucasian specimen and which ones correspond to an African specimen. So look at the curves. Maybe one would say that, okay, these 2 curves here that have higher reflectance, maybe those are the curves that correspond to the Caucasian specimen. But turns out that's not, okay? So in fact, if you look more carefully, you're going to see that one of the curves associated with a Caucasian specimen is lower than one of the reflectance curves for the African specimen. Just indicating this terminology of Caucasian, Asian do not help much. So perhaps we should go straight to the level of pigmentation and avoid this altogether. For example, there are other situations like tanning, for instance. We have our constitutive pigmentation, which is determined by genetic factors, and you have facultative pigmentation that is affected by environmental factors, like, for example, exposure to ultraviolet light. And this can change a lot, okay, throughout time, our lifetime, and even in periods of few days, if you go to the beach, or years, okay, and of course, measurements can be affected by that. So in the case of skin, okay, or other tissues is get complicated because there are other issues at place, okay? But how about, for example, sand, okay? In theory, you could measure this much easier in lab, okay? We don't need to deal with health protocols and regulations and so on. So what you like to have? For example, like to have information about the amount of iroxides. For example, iroxides are the impurities, okay, that give color to sand. For example, you can have hematite, goethite, magnetite, and even though the amount is very small, like 1.5, 2% is enough to give the color. We want to have, for example, information about the grain size, shape, porosity. This is a kind of parameter that's very difficult to measure because once you manipulate the sample to get the porosity measurement, you change the rearrangement of the grains and you change porosity. Another thing that you like to have is information about the degree of water saturation, okay? For example, these 2 states here, the intermediate state and the state of dry water films, they have very similar spectral responses. However, they are very different when it comes to support plant development. So in practice, that's what we have. And this is a very good database. It has lots of curves. I'm putting here just, okay, the visible range, but the curves go from visible to infrared, okay? And what is provided for us in this database? The description is reflectance of a sand sample obtained from a hematite-rich dune from Australia. And they provide a photograph of the sample, which, by the way, is very helpful, okay, to guide, for example, try to gauge the amount of that iron oxide there. And again, they don't provide more information, perhaps because they didn't need for their own purpose, but we would need that. And we don't have. So the best that we can do is to use average values for the other parameters available in the literature, obtained from measurements that have nothing to do with the spectral measurements that we are using. How about, for example, elementary data to do the simulations? For example, we talk about these iron oxides that are very important, like hematite. Being a very ubiquitous material, okay, one would assume that hematite, you can find the data very easily. And in fact, you can find many sources for data for hematite about its refractive index or extinction coefficient. The problem is that many of the sources are very conflicting. Within the same spectral regions, we have different curves. So which one we should use? So it takes lots of time, detective work, to determine which ones are more reliable. So, and this takes time, is another issue that one has to address, okay? But there are not only bad news, there are also good news. So in 1993, a group of labs in Europe, okay, people that are interested in remote sensing, very strong people in this area, they realized that they need ground-based data to help the evaluation of their models. And they make a huge effort. Several labs, they collect many samples from different species, more than 50 species of trees, crops, and so on. When we say 50, well, it's a small number. We have, hundreds of thousands, millions of species out there. But believe me, that was already a big step. And they measure, for example, reflectance and transmittance, did very careful measurements of that and make all the data available. But more importantly, they also measure this characterization information, characterization data for the samples. The thickness, fresh and dry weights, concentration, absorbers, and so on. So this was something very unique, okay? And we want that, if possible, to be replicated in a large scale for other materials. But how about elementary data? So in the case of plant leaves, we have this nice database, reflectance and transmittance there, and we have the characterization data. So chlorophyll, for example. Chlorophyll is a very important pigment. All the life in the planet depends heavily on that. So one would assume that, okay, it's no problem here. We can get data for chlorophyll anytime that you want. So if we go to publications and trying to find data, absorption data for chlorophyll in the standard way, for example, using one of the standard methods, light absorption spectroscopy, you go one paper that cites another one, and keeps going like that until you find to the mother lode, the ones that really did the work. These guys here in the 40s, okay? And they measure that. And they did a very careful work, but they have their own technical limitations at that time. And if you think, I want you to pay attention to this region here, the curves get a little bit overlap each other, indicate some poor sensitivity in that area. We are going to see the effects of that soon. We can have also another approach. For example, imagine you have a model that has been evaluated and you are confident the model is reliable, then we can generate reflectance and transmittance curves and adjust the absorption curve. And then you can have a good approximation. For example, in this case here, they got approximation for chlorophyll A and B. More recently, the same authors, same researchers, which are very important researchers in this field, they were able to even separate them, chlorophyll A and B and so on. That's another approach. But keep in mind, that's an indirect approach. We are using a model to get these curves. Another approach that we have is photoacoustic absorption spectroscopy. Basically, you send light, you have the sample in a chamber, and everything that's not absorbed is propagated back to that chamber in terms of heat, is picked up by a microphone, and you have the signals there. So we can have curves here, and you have very good separation between them. You have the three curves, but there is one important detail here. You have not the absolute units here, you have relative units. You have the signal here. So you need to normalize this somehow, and this is not an easy task, okay? So what happens then? Now, look at this. All these curves, we have the measured one from Lopex, okay, and you have three model ones. All three model ones were obtained using exactly the same model, exactly the same parameters. The only thing that we changed was that chlorophyll from these three different sources. And you see how the curves vary. For example, the one that people use it, the more traditional one, light absorption spectroscopy, you have all these jags here, which are related to that lack of sensitivity in that region of the spectrum. And you see that in published results, sometimes the curves are in the papers are very small. And here I'm showing a range between 400, 700. Sometimes the range is from 400 to 2,500. You don't see that very well. But there you go. Even chlorophyll, we have this issue. Imagine for other pigments, okay, that are not as common, is even more difficult to find data that is unambiguous, okay? But the issues, they do not stop there. For example, we have in vivo and in vitro difference. In the plant, the chlorophyll is within the organelles, the chloroplasts, all over the leaf tissue there, okay? So when you are trying to measure the absorption for chlorophyll, first thing that you need to do is to put this in the solution and separate the pigments using chromatography. Once you have that, you put in a solution again, and then you measure, okay, the absorption spectrum of chlorophyll. The problem is that in the in vivo situation, you have Sieven-Detur effects that we showed before in the video about the skin there. Okay, they affect the absorption in comparison to the absorption of a solution. So the absorption within a solution is different from the absorption under in vivo conditions. Another important factor here is that in the solution, you have a substance there, for example, could be acetone, okay? And that substance interacts with the protein of the chlorophyll. So you have small changes, and these changes translate to spectral shifts. So 5, 10 nanometers, both quantitatively and qualitatively. So in other words, the difference between in vivo and in vitro are significant. We have another approach that we can use. For example, we can use an inversion procedure. So let's say now that we don't care about specific absorption of the chlorophyll in carotenoids. We are not using a first principles approach. We want the absorption of the whole tissue here. You have, for example, here the mesophyll of a soybean leaf, okay, and you want to get the absorption of the entire tissue there. One thing that we can use is that we have a model, we measure reflectance and transmittance, we put this as input in the model, and we get then the absorption and scattering coefficient. There are, of course, some issues here. First, not all models are prone to this. If you have a model that's non-deterministic, can be really be a big challenge. You have to measure this as well. So that's another issue. But the most important issue here is that, was that model properly evaluated? Sometimes data obtained through these inversion procedures using models, okay, nobody knows too much about these models. They're like a black box. Oh, I published this model in such and such paper, but you look at that, you don't find anything about how it was evaluated. So in many cases, you cannot trust this very much. Not all the cases, but in many, okay? Other issues here, for example, these databases, even though they are very valuable, okay, the ones that we have out there, the field that we have out there, in many cases, they don't give too many options, for example, in terms of light incidence and collection geometries. For example, the skin spectral database, there was just one angle of incidence being considered, 45 degrees. LOPEX, only one angle, 8 degrees, which can be explained by the fact that since they are interested in remote science applications, they think about, from a satellite point of view, that may be one of the reasons, okay? But we have just one angle of incidence. When it comes to BRDF, BTDF, BSSDF, even more complicated, okay? Then things get even worse because the number of databases is really scarce, okay? And the characterization data, all this information, the lack of information also applies. But I want to stop a little bit here and talk about make a slight digression here, okay? Look at this name, Woolley, okay? Probably none of you have ever heard about this researcher before. Someone told me at some point, another professor, old professor, that at some point of our careers, we need to make a decision. Do we want to be famous or we want to be useful? So this fellow here, probably he decided to be useful. Nobody knows too much about him. I tried to find information. I know that eventually he became emeritus professor at the University of Illinois. But what he did was spectacular. He did an amazing work. He did all sorts of measures for plants under different conditions, the morphology aspects as well, what happens when they are subject to water stress. So every time I see papers on this guy, I said, oh man, thank you very much. And I have copies, hard copies that they're almost falling apart now. Okay, so that's one of the cases that you do fundamental work and you may not get recognition immediately. But here, 50 years later, we are still talking about him, and probably we'll still be talking about his work and his data many, many years to come. Okay, so you have data out there, some data is published, and you need not only the data, but in order to reproduce the results, you need information like angle of incidence, collection geometry, spectral resolution. In the case of BRDFs, which was the wavelength that you used. If you don't have reflectance, for example, you have radiance, you need also spectral characteristics of the light source. Unfortunately, one would assume that, okay, everything has to be provided, but sometimes it's not, just because people forget. It's not something that they are doing this because they want to hide something. And you may try to contact the authors and you get information, sometimes you don't, okay? So that can be a big problem. There are other aspects that are even worse or more difficult to find. For example, let's take a look at blood, for instance. So when blood is flowing, okay, the motion of the blood can affect the optical properties considerably. For example, we have the shear rate, which corresponds to the velocity gradient in a direction that's normal to the flow. If you have low shear rate, all the cells are moving in a kind of random fashion. As you increase the shear rate, they start to roll, tumbling, all sorts of movements. Eventually, they become aligned. And of course, this depends also in the fraction of the blood occupied by the cells, the formed elements. And depending on the shear rate, okay, we have different CV-detour effects and affect the optical properties. So in order to reproduce some measurement, we will need to know this as well. And this is another piece of information very difficult to find. So we talk about reflectance, transmittance, and BRDF. Let's talk a little bit about subsurface data. As you can imagine, it gets even more interesting, okay? So let's talk first about two guys, also like Woolley, they did amazing work, many years ago. And what they did, they grabbed skin specimens and they measured subsurface scattering. So it was an in vitro process and they got measurements for few wavelengths and so on. Okay, and it doesn't seem much because they just took a few samples, and few measurements, and how, skin being also a very ubiquitous material, we would assume that we have tons of data for that. But it's not the case. And in fact, we even tried to contact them. I contacted, for example, Bruce, and he was very surprised that decades later, we're still using his data. He works now for IBM. I think he was a student at that time. His supervisor was the other fellow, van der Leyen, which was a very important name in biophysics. Unfortunately, he passed away a few years back. Okay, but they did these measurements, which are very useful. And one of the things that happens, one of the side effects, is that they also made some suggestion in their paper. In the paper that they published this data, they say our data here could be approximated by a function. They did not provide the name of the function. They just provide a number, which was a function in a table of functions in a book by another fellow named Van der Hulst, another big name in terms of scattering. Okay, and this function was the Henyuin-Greenstein phase function. So what is this function all about? These two guys, Henyuin and Greenstein, in 1941, they have lots of data about Mie scattering from galaxies, and they want to fit the data in a curve. So they come up with this curve to fit this data. So they never thought that their curve were going to be used by simulating other things. It was for Mie scattering from galaxies. So what happened then is that people start to think, why am I going to measure other tissues, other materials, if I can use this function, right? So this function is very straightforward. You can obtain, for example, back scattering lobes, forward scattering lobes. You can even have both at the same time if you combine two functions of these, a weight average of them. But there are pros and cons of this. So they are relatively to use if you are going to use this, for example, ray tracing. And certainly they can make papers look really cool, right? All of a sudden you have this function used for galaxies. Wow, man, that sounds very scientific. But what happens? They are not based on the mechanics theory of scattering. They don't have a biophysical basis. So if you start to generalize this for different materials, plant leaves, sand, different specimens, and so on, you are really stretching here. We are getting far and far and far from a first principles approach. And in many cases, the fidelity cost ratio of this approximation is much lower than simple approximations, like, for example, exponentiate cosine that we use a lot, for example, in computer graphics. Another interesting thing to mention here is that when the data is there, is published, and you think, okay, great, let me get the data here. And is in the graph there, and maybe you can contact the authors. Sometimes the author is going to say, okay, I don't have access to that data anymore. Unfortunately, the data got lost. The only thing that you can do is to grab the data from the paper itself. So you have to go there and use some tools like Ginput in MATLAB and so on to grab the data yourself. So don't expect to have that data in a plate, for example, Excel file and so on. So sometimes you have to go there and make all the conversions yourself. And it happens quite often. So let's talk a little bit even deeper than that. For example, materials inside the different tissues. For example, collagen fibrils that we have, for example, in our skin, in our eyes, and things like that. Some time ago, we want to reproduce the appearance resulting from cyanosis. Cyanosis, you have that kind of grayish, bluish appearance of skin that can result from different medical conditions. So there is a lack of oxygenation, can be different things, can be even very serious things like heart conditions can cause that, or hypothermia and things like that. So, and we choose to simulate that using the fingertip because it's a hypopigmented area, so the masking effects of melanin are not present, so we could test that better. And we tried to test that, and we could not get those colors, those chromatic attributes from cyanosis, okay? So several people mentioned that never been actually demonstrated, without beyond any doubt, but they suggested could be some Rayleigh scattering taking place, okay, in some layers of skin, the papillary dermis here specifically, where we can encounter these collagen fibrils, okay? So one of the key parameters in this case, if you want to simulate Rayleigh scattering there, you need to know the diameter of these fibrils. And we use the data that most people are using. There was a technical report available on the internet from a person that's very well known in biomedical optics, and there was a value there, 100 nanometers, and we use that. And okay, so no difference. And we start to think that, okay, maybe the model does not have this capability. And a good sign, or in a bad sign, of a model is doing a good job, is that if you can reproduce a behavior that you are not, planning to reproduce in the early stage of the model development, okay, a counterintuitive, for example, behavior. And we said, okay, maybe there is a problem there. But eventually decided to, okay, wait a second, we are kind of not following our own methodology here. Let's go deeper on this. Instead of using this data post in this technical report, okay, let's try to find the data ourselves. And we start to dig, and eventually we found a paper, okay, from some Japanese researchers in the late 80s, early 90s. They did lots of measurements, and they showed that using electron microscopy, okay, that these fibrils can vary between 20 to up to 120 nanometers. So then we saw, wait a second, we have a wide range here to experiment with. So eventually we were able to capture, okay, not only to capture the chromatic attributes of cyanosis, but demonstrate, okay, that in silico, that Rayleigh scattering was an important part of this process, not only the level of oxygenation in the blood. And we extended this later, and you are able to demonstrate as well that similar mechanisms would affect, for example, and result in the bluish appearance of veins. Okay. In the first work here, we use Helios. In the second one, we use Helios for the skin and use seal blood to simulate the vein. Okay, we are talking about data that's being collected in laboratory and things like that. How about remote data? Okay, so recently, we are working in the development of a mode of light transport for snow. And besides the evaluation against ground-based data or data measuring laboratory, we want to also compare with remotely acquired data. So in this case here, what we use data provided by the AVRIS instrument. And what we have here is the Himalayan region. The data comes from this small area, and more specifically from this little area here, which is an area composed of 5 by 5 pixels, 25 pixels. What you have here in this curve, the error bars indicate the variation of the curves, and the squares, the average information there. So one of the problems there is that in order to try to reproduce these results, we need to know the angle of incidence. In order to do that, we need to have information about the terrain geometry. So what's the elevation there? Another important factor here is atmospheric conditions, because if you have lots of cloud cover, it's going to affect, the readings. Sometimes you see data sets from these regions with kind of holes, gaps, because the atmospheric conditions were not very convenient at that point, and people decide to omit that data because they were not very reliable. So to deal with these issues as well. So how about data acquired from another planet? So like data from Martian regolith, for example. This is a very important area of research because it tells a lot about the evolution history of the planet, and also this material like dust and this regolith can affect also the measurements from other instruments if they are deposited on the surface of other instruments. So one of the things that we needed to realize from the beginning is that we don't have access to Martian soils. We can have samples from meteorites, which are very, very expensive. The best people can do is to work with what's called soil simulants. And there are lots of similarities, between some soils on Earth and soils on Mars, but there are key differences. For example, in Martian soils, like here on Earth, you can have iron oxides like magnetite, goethite, hematite, and so on. And the weather information of these materials seems to be similar. So we can have from wind transportation, water transportation, and this affects how these iron oxides, for example, are present in the grains. They can be mixed with the core, can be forming coatings, or it can appear just as pure particles here. But there was one key element that we are not sure yet, the core material. Here on the terrestrial sands, we know that we can identify that. We can get sand, you can see that. Most of the time you have quartz, So what happens, on Mars? So what happens that is a little bit darker, So which suggests that it's not quartz there, but another material. One common material found in the surface of Mars, based on the spectroscopic measurements done remotely and in situ there, is basalt, So in 2004, in the Spirit rover mission, they have a camera, multi-spectral camera in the rover, like 1.5 maybe meters, from the ground, flat ground at the Gusev crater, and they made some kind of measurements there of from that soil. So we tried to reproduce that using one of our models, the splits model, And first we use basalt here. And the curves got really, really low, indicate, maybe we are not in the right track here. Then we use, just for comparison, quartz, which is very high. So what's happening here? Maybe the model has many more imperfections that we thought about, maybe was not going to be able to reproduce that. But there's another thing that happened, another serendipity factor that happened at that time. During that mission, one of the wheels of the rover got stuck and started to drag the terrain and reveal some soil underneath the regolith here. Very white soil, indicating silica-rich deposits there. And then we start to think, perhaps one of the core materials may be formed by this material. Some of the particles can be composed of this material as well. So that's what we did. We start to use for some of the particles, some of the grains, silica-rich basalt compositions, and for others, basalt. So at that point, we start to get close approximations there. All the other parameters, like grain size, shape, and so on, we had to use, for example, things that we know average values in the literature for terrestrial sands. Some parameters like porosity, we could use something a little bit better. We have some values, approximate values for porosity in Mars. So, but most of the time you have to use data for terrestrial sand. So what can be done with these data-related issues here? So first of all, we can keep probing the literature. I think sometimes we dismiss what happened before us, but turns out that people, especially when they have no access to computers and things like that, or TV and things like that, Netflix, they spend lots of time in the lab and they did awesome job measuring lots of things. So you can find very good data out there. But one of my suggestions is that don't stop in the first reference, go and find the original source, first-hand information. Sometimes the best thing you can do is you're not going to find all the data that you need in a single source. For example, water, okay, a very common ubiquitous element. There are very good measurements for some spectral regions and other measurements that are very reliable for other regions. So, for example, the data that you use for water is a composite data set comparing from data from different sources measured under the same conditions, same temperature, and so on. So whatever you do, okay, eventually you need to use, for example, average values or values that you can find in the literature. And the literature provides range. And the best you can do is to work within those ranges. Of course, if you want to fake results and do something that's not very honest, you can go outside that range. But if you are going to do something that people maybe can use in the future, you want to stay within those ranges. And then you can get good approximations. Does not mean the model is really great. It's just it's worked well for those values. Maybe when you have data and you have characterization data measured for that spectral data, you can have a better idea whether or not these models are really good or not. So there is another possibility. How about getting our own data? There are two big benefits here. We have full control of the measurement conditions, and you can have a wide scope of contributions, like I mentioned, Woolley, for example, and others. Our work, although it's going to be lots of hard work, it can last many, many decades. But sometimes this may be the only option. For example, at some time ago, we did some research about fading, yellowing of paper. So this lignin in the paper start to transform due to exposure to ultraviolet light. And we need data for that. We look for several sources. We could not find any source that you can really trust in terms of the spectral resolution and reliability and so on. We decide, okay, how about we measure this ourselves? It's just paper. Come on, you just can, expose to ultraviolet light, do some measures along during the time you can get this. So the problem is that we need several things. Equipment. So we didn't have a measurement device. We have to borrow one from another department, an old one, have to learn how to use it. We didn't have a lab at that time, so my student had to do this in his basement. And lots of time to set up the equipment, things like that. Eventually, we got a better equipment, but you had to go through the whole process, preparing the samples, do the measurements. And because this phenomena takes place over time, okay, takes several weeks. And at the end, if you realize that you did something that's not correct in one of the parts of this process, you have to repeat everything again. So that can cost months and months. And that's what happened to us, okay? But things can get even more challenging when it comes, for example, something that's organic, especially human tissues. Then you have all the other things to think about that. For example, ethical things, protocols, and so on. In that case, the best that we can do, okay, is really use data measured by people that have really a strong infrastructure to do that. So I'm going to show now another video, okay, that shows one of our recent researches in which we actually use data for human subjects, okay, heavily. And it was very important. Without that data, we could not have done this research, okay? So I was wondering if you could play the second video, please.
Over time, the appearance of real materials can change due to different environmental factors. Among these external stimuli, light plays a central role. As we are exposed to ultraviolet radiation, or UVR, our skin undergoes a series of physiological processes that can lead to noticeable appearance changes, commonly referred to as tanning. Besides enabling the predictive reproduction of these ubiquitous time-dependent skin responses, physiologically based simulations of tanning dynamics can also play an instrumental role in the design of new procedures for the evaluation of sunscreen's efficacy, especially considering the recent legislations limiting in vivo testing of these products. Skin tanning dynamics involves primarily the stimulation of melanin production and skin thickening. The produced melanin is distributed throughout the epidermal layers, with some portion being eventually removed through natural decay. Depending on the biophysical characteristics of a given skin specimen and the UVR exposure dose, different tanning responses can be triggered. Accordingly, the proposed framework takes as input skin biophysical parameters and UVR exposure doses. Initially, the exposure doses are evaluated to determine whether they are sufficient to trigger a tanning response. Simulations are then performed to compute the updated values for the biophysical parameters of interest. These are then used in the synthesis of images depicting tanned skin. Alternatively, the updated biophysical parameters can be used in data-driven investigations of skin-related photobiological phenomena. For more details about the framework's formulation, please refer to our paper. Measurements considering a specimen subjected to 3 distinct UVR dose exposure schedules were used in assessment of the predictive capabilities of the proposed framework, with the simulated results showing good agreement with measured data. We then use these datasets to illustrate the resulting skin appearance changes over time. We also employ them to demonstrate the framework's capability to account for the lower UVR sensitivity of specimens with a higher constitutive pigmentation level, as well as their higher tanning ability when subjected to exposure doses scaled according to their respective sensitivities to UVR. We note that the updated biophysical parameters resulting from our simulations can be employed in image synthesis pipelines based on the use of different models of light and skin interactions and distinct geometrical representations. Hence, the proposed framework can be effectively employed in the production of animations depicting time-dependent tanning responses. Building on the current knowledge about tanning dynamics, we have developed a novel physiologically based framework for the simulation and visualization of this complex phenomenon. It is expected to contribute to advancements in realistic image synthesis by expanding the spectral and temporal domains of material appearance reproduction, and to serve as a platform for interdisciplinary investigations involving skin responses to photoinduced processes.
Okay, thank you for playing the video. So this example of this research here, without the work of different people in this area, is an area that's not widely explored. Okay, there are lots of things that we still don't know too much about in terms of tanning, and involves actually experiments with real subjects, exposing them to ultraviolet light that can pose risks. So we had no infrastructure, no expertise to do that in a safely manner. So we have to rely on data that other people have been measuring. Okay, so that's just to illustrate how important this thing is. And without this data, this research here could not be possible. And it's one of the first really physiologically based framework that allows the visualization of this phenomenon. And without this data, we will not be here. We'll be able to present this today. So what's the situation then? What we have? Okay. First of all, okay, the original question: do we have enough fundamental biophysical data? Okay, and my perspective, my answer is no. Okay, why we don't have this data? Many reasons. There is first that dilemma, right? That collecting data and measure data like this is like basic research, and there is the dilemma between basic research and applied research, and sometimes basic research is perceived as something that's not going to bring benefits in the short term. But sometimes people forget, in order to get that applied research going and bring these benefits, you need the foundation. Okay, without the basic research, we don't have a strong foundation. We cannot get too far, right? Another reason, and I gave an example here of generalizations, for example, if you look at the timeline, when some of the measures, some areas stop to be performed, you know, like is a kind of coincidence, overlap when the time that computers became more pervasive. It seems that for some groups, it became easier to do simulations than just go there and measure, okay? And I'm not talking about people that only do simulations, even people who do the measurement themselves, right? But that's one of the many reasons, but the fact is that you have these issues, okay? Then the second question becomes, should we stop everything that we are doing? So we don't have the ideal situation. We don't have all the data that we need to test, evaluate all the models, okay? Again, my personal opinion, no, okay? And why not? So if we are going to wait, okay, for the perfect situation, it may never happen. And you have plenty of examples in science that people just move forward. Okay, that's a way, okay, to try to break the ground. Okay, of course you are the first in certain areas. You are the first to get the, you know, the rocks and things like that. But you need to proceed. You need to go for it, and also need to be realistic, right? There is this quote from this famous British mathematician that works in statistics. And that this quote can be summarized that all models are wrong, some are useful. And he is not that far from this, for example. Let's look, for example, an example of a plant leaf. Okay. So it's a very complex material. We think that's so simple. You can easily, you know, simulate what's happening here and get measurements and so on. But just to paraphrase someone that's much more knowledge than I am in this area, okay, is a very complex, okay, material. Combinations, optical combinations are fantastic. So it doesn't matter how good, how detailed our model is. In one of our models to simulate plant leaves, ABMU does a pretty good job, okay, compared to other models out there. But still, we are not going to be able to get probably everything that happens, okay? And one of the constraints is the data. But what I think is that as more data becomes available, we can make the models even better, okay? You can increase the effectiveness and we can trust them more, okay, that they are doing a good job and they can continue to support research in different areas. In order to support the research, again, like I said, we need a strong foundation and we need these models to be, okay, well tested, well evaluated. So, realistically speaking, is there any light at the end of the tunnel? Probably not in the short term, okay? Support for this kind of initiatives is not big. So one of the reasons is that this type of research sometimes is not considered flash enough. And that's not only just my opinion. So if you talk to people, for example, at some point in a conference, I talked to someone that was very well known in remote sensor vegetation, and I asked her, okay, we are here in this workshop, talk about remote sensing and this mission and blah, blah, blah. So how about ground truth data? Everybody's complaining about that. And she said to me, yeah, we send proposals and we get rejected. And the proposals are not, and that I quote her words, sexy enough, right? Flash enough. So, but there are some, changes in the horizon. For example, some institutions, some companies are realizing that they need that if they want to advance what they are doing. For example, the NIST, Xerox, for example, they are. I heard, that I understand that they are compiling database for human skin, and for example, have recent publications of NIST talk about reflectance spectra for human skin from the ultraviolet to the infrared range. That's a very good sign. Just to give an example, the data that we use to evaluate our skins, skin reflectance in that video that I showed in the beginning, that data was from ultraviolet to the infrared range. We compared that data that was published in 1955. That was the best that we could find when we develop our model in 2015. Okay, so that gives just an idea. But the thing is, what we can do about this, because we are not equipped, most of us, with labs to do that and change this dramatically. We are doing our work in our areas, which is equally important. All different areas of research are important. No area is more important than the other, because if you want to advance, you have to advance in all the areas, okay? But so what we can do about this? First thing, I think, my personal opinion, we have to keep an open mind about interdisciplinary research. Is a big buzzword. All these grant agencies, they say, oh, let's, make some support to interdisciplinary research, innovative research. In theory, yes, okay, people say that. But in practice, if you are working in a frontier or different fields, chances are that you are going to be hammered by people from these fields instead of being praised, okay? And takes long time to mature interdisciplinary research, long time to publish. And like I'm illustrating this talk, right, you have to go sometimes completely outside of your comfort zone, dive into other fields, and you need to realize that and really, value interdisciplinary research, okay, not just use as a buzzword. So in that case, for example, we need to be support to other colleagues in different areas that are trying to change this. For example, sometimes we are going to review a paper and these guys publish a data, for example, transmittance for a given tissue there. Maybe it's not the best possible data. Maybe something is missing, okay? But let's give support. Let's give some encouragement. At least is the first step, right? Let's, give some incentive for people to continue to do this. That's, again, is just my personal opinion on that. But we need to realize that if you want to solve this, we need really a collective effort. Is not going to happen in the short term. It may take a long time, and we can only change this together. People from different fields, different areas, different views. Okay, so just before I conclude the talk, I want to thank first and foremost my graduate students that developed these models along the time. Not all of them I cited here, and before they get angry with me, is not in particular order, it was just a random order there, but these guys have done a terrific job, and I'm very grateful to them, and also people that we use some images from during this presentation. Also, a very important mention here, my gratitude to people that work in these areas and to collect this data. Many of them have been mentioned during this talk, and like I said before, without their efforts, we could not have developed any of these models. Probably I will not be here today for sure, okay, talking to you about this. And I'm very grateful. There are many others. I just included here some of them that I cited during this presentation, also not in any particular order. With this, I conclude my talk. I hope I didn't bother too much, and I hope that you could understand what I was saying, despite the fact that I talk a little bit too fast sometimes and the accent is not that great. Okay, so if you have any questions, I'll try to answer them.
Thank you, Gladimir,
All right,
for the great talk. You gracefully cover applications from Mars to plant leaves. It's amazing. It's amazing. Now we're gonna start the round of questions. Remember, you can send the questions for YouTube chat and Discord channel as well. You have questions? The first question comes from Marcelo Walter. I believe that most measurements are performed based on their utility to related area and therefore do not have everything you need in CG. Have you given up some line of work due to lack of data?
Okay, first part of Marcelo's question is completely right. That's one of the things. So one of the things that you need to keep in mind here, okay, when you talk about these issues, that is not just as a criticism to people that come up with the data sets. They have their own needs. They didn't need, for example, the grain size for the sand. They want to use that to interpret what's happening in the desert in Libya, for example, for some reason, okay? So that's true. And in terms of giving up some areas of research, I think the main thing here is really to find people to work with that are really motivated. In some cases, we had to. For example, I can give an example. At some part, we try to work, for example, with paper. See, paper, very simple thing. And we need to get data for that. And we found publications. And we contact some organization here, okay? And I'm not going to mention any names. I don't want to be sued by anybody here. But I went there and visited them and everything, and they were saying, oh, yeah, we need to support some research. We have some kind of say in some grants here. But then they start to be a little bit, defensive in terms of releasing their data, start to put some conditions, okay? Then I told my student at that time, Francis Chen, which was in these two videos here, I told Francis, you know what, Francis? We have to rely on ourselves here. Rely on these guys, willingness to disclose the data for us. Let's try to find a topic in which, despite of the limitations, we can find something. We already have done some work in skin with Aravind, my other student, BioSpec. Let's move further on this. Let's make this area go even deeper. So that's when we decide to go from paper to skin, okay? And that's one of the occasions that we decide not to follow a particular area. We prefer to take our chances, what we have out there, than to rely on other people giving the data to us, allowing us to access the data. Okay. By the way, at some point, one of the reasons also that we talked about, we did some measurements, for example, for paper as well, to compare these different approximation functions, phase functions, like the Rinewin-Greenstein phase function, exponentiate cosine. Francis did some measurements of that, okay, using lasers and things like that, and he published that in our optics journal. And he did that in his basement. So we borrow a laser from someone, camera from somebody else, okay? But then if you want to do more, for example, the size of the fibers inside the paper and the distribution, then we need really, really detailed data. So that's why I decided, no, let's switch to something else.
Okay. Next question comes from Anatoly Lashuk. This is a brand new area in CG. And how about the mathematics? Anything special needed?
Okay. First of all, I want to say that, I was very fortunate, not just because I have good students, but more important, I have very, very good supervisors, okay? So I have guys that are really inspiring role models. And Professor Anatoly Lashuk was my supervisor and a great friend. And I think is one of the wisest person that I ever met in my life. So everything that I did in research in my career, okay, I really came from him. So from his model, his inspiration. In terms of mathematics, I think there are lots of things that can still be done, okay? There is always room for innovative approaches. I want to mention something here, okay? Some of these models, we apply a very different approach. For example, for sand, for blood, okay? So we don't have all the elements stored in memory. They are generated on the fly. We interact as accurate as possible. Each element, we discard, generate another one. This allows two things. First, very fast, you don't need to spend lots of memory. Much more fidelity on this, okay? And this is a completely innovative approach developed by one of my students that I want to give the name here, Bradley Kimmel, okay? So, and that when we start to work with sand, we are going to use the same approach. For example, we are going to send some layer model and the traditional approach. And he came to me and said, no, why we don't do each, grain of sand here? And he developed that. He developed all the mathematical framework for that, all the theorems and things like that. He has a degree in pure math as well. Okay, so and we have been exploiting in a good way what he has created. Okay, and I'm sure that there are other innovative ways to do things. Okay, that people can come up with that can make our job much easier, and you can go even deeper. Give an even deeper level of abstraction of the materials that you try to simulate.
Okay. Next question from Ricardo Marroquin. What do we have to look for when using data from others? Sometimes, or even often, they contain issues. For example, the Merrill material data set is widely used, but some issues were only found more than 10 years after.
That's a very, very good question, right? Some of the issues that you have, you can note right away. Some pieces of information describe how the data was acquired can give some clues, or some information is missing. Sometimes when you are actually using the data, then you realize that. For example, I gave the example for this data from the Avery's instrument. Okay, so when my student was looking for the different curves, he had to find the ones that have very good information about atmospheric conditions. But before that, we tried to use other data sets, and you have big gaps, and we could not understand. Eventually, realize that was because of poor atmospheric conditions. That was not informed in those databases. We need to realize that. Okay, it's a very difficult question, Ricardo. So I think it depends a lot what your intended use for the models are. Okay, but as you are using the data, you start to get a little bit more, questioning more about the reliability. For example, one of the things that I mentioned is the extinction coefficients and refractivity index of hematite, for example. We got the data there, we start to use it, and we start to get very weird results, okay, in the model. So something is not right here. We try different things. No, let's look at this data. Then we saw other source. Even with water, there was recently, my student worked with snow, the Trivarsa that's developing this model for snow. We are trying to reproduce some features in the infrared range, and we note some spikes there. And then you realize that some of the data sets that they are using for water has some issues there. Okay, let's look for a more reliable one. I think, unfortunately, sometimes you have to go bite the bullet, start to use it, and then, if you are lucky, you can detect this early on in the game.
Okay, next question from Natalia Pizol. Professor, do you see this research being applied to e-health solutions?
Absolutely. So the thing is, Natalia, so let me tell you this. Lots of devices that we try to use that, like it or not, they have embedded some simulation, some computer model. Let's, for example, talk about the most used device in AR, for example, emergency unit in hospitals, the pulse oximeter. What do you have there? You have infrared being transmitted to the skin, right? And you have some algorithm that decodes that information. Then you have the level of oxygenation. And you can go on and on. One of the key things, for example, and I have to be very careful what I say here. Again, I don't want to be sued by anybody. Okay, for example, we have skin cancer, right? So, and there are lots of, this is the holy grail in the dermatology, how to detect this early on using, computers and things like that. There are all sorts of works in this area, even people proposing devices. And of course, inside that device there is a computer model. So then you are going to think, okay, this device is going to tell me that this lesion is cancer or not. So what do I know about this computer model? Sometimes the companies do not release anything about the model. It's a black box. Are you going to trust that result from that device? Probably not. If it's me, I prefer to go there and take a biopsy. Okay, now I cut my skin here, but I'm not going to trust this. So if you want these devices, okay, using different areas, for example, we have done lots of research in this area as well. For example, we have done research, for example, to differentiate two diseases, okay, related to blood, methemoglobinemia and sulfohemoglobinemia. So there are two substances that cause problems, okay? So, for example, you have the cyanosis as a visual appearance, and the blood start to lose the oxygenation capability. One of them, okay, you can treat very, very easily. You have a methylene blue, a substance you can give to the patient. The other one, you need a blood transfusion. But both are very, very similar. So we were able to determine that in some kind of spectral band, they differ, and you can actually pinpoint exactly that. Okay, so that is an application. These medical conditions are not very common. Okay, so we are not going to find them everywhere, every day. But, one can easily get these conditions, okay, very easily. For you to take some kind of, product in your home, you don't know, maybe there is a compound there. For example, methahemoglobinemia was a big problem in the US in the 50s because lots of fertilizers in the ground drained and went to the water supply, and people start to have that. Okay. So you use models in all these different areas. Another thing that was mentioned in one of the videos, there's lots of regulation nowadays that are completely banning in vivo testing. Okay. So you cannot test in human subjects anymore. You need to do this, what's called in silico testing using models. And these tests are only going to be reliable if you have any kind of measure of their fidelity. I don't know, maybe I went too far here in your answer, but sorry about that.
Okay, very nice. We are running out of time. So the last question, it comes from Marcelo Walter again. Some suggestion of low-hanging fruit line of work in this area?
Oh. Oh boy, there are lots of low-hanging fruit here, okay? So we are trying to collect them, Marcelo. So for example, we use the Helios model for anemia, we use that for cyanosis, we use that for jaundice. But the fact that we use our models in these areas doesn't mean that we solve those problems. There's plenty of rooms. There are lots of unknowns, okay, that can be explored in this area, for example, in the biomedical area and things like that. Okay, for example, one of the things, okay, that Marcelo used to work a lot is a big expert textures, right? So, and most of the models that we deal with, okay, when it comes to the BRDF, most of them are isotropic. So we take into account only the angle of incidence, only, okay, the polar angle, not the azimuthal angle. So we do a very poor job in that geometry on the surface of the materials. So this is an area that's huge, room for improvement. So, for example, in our models, okay, for skin and plant leaves, what we did for the surface was very simple. We could not do better than that. For example, Alan Fournier, okay, which was Marcelo Walter's supervisor, one of the big guys in computer graphics, in my opinion, one of the examples for all. He was one of the few that did something about this. With Poulan, they did some kind of simulations for the anisotropy of the materials, okay? We even thought about using that, okay? But lots of room for research in that area, But again, in order to validate your results, you are going to have to really, dig really deep to find, for example, measure BRDF data that have information not only about the polar angle, usually they have only the polar angle, but also about the azimuthal angle. But there are lots of areas, I think, that could be explored. I think that one could have room to do research for many, many years to come.
Okay, I want to thank you, Gladimir, again. Thanks the audience for watching. You can talk with Gladimir in the Discord channel. Stay tuned for the next technical session about computer vision and applications. See you soon. Bye.
Thank you very much, Afonso. Thanks, everybody.